Welcome to AFD'S Academy. Today, we're going to solve a series of questions on volumetric analysis, calculations. I'm trying to make it intense that we're going to cut across all the basic things we need to know. And we've discussed about the formulas already. I believe by now we'll be able to apply the formulas whenever we come across them. As such, I will have to go around solving a whole lot of questions that you'll be able to see how those formulas are being applied. So, let's start with our first question today. I will read it and now give us the given. That's what I would do, but I wouldn't be writing the questions themselves because it's going to take us a long time to do that. So first question here, we say 28.0 cm cube hydrochloric acid of concentration 4.1 GDM cube neutralized 25 cm cube of an unknown alkali YOH, whose concentration was 7.0 GDM cube. We should calculate the molar concentration of YOH. The Y is unknown, remember that. The relative atomic mass of the element, and name the element if possible. So when we're done, we should be able to name what element it is. That is the Y. As such, when we put it into the formula, the YOH will now have a name. That's what they're trying to say. So let me list out the given first. We have our A, which is HCl. And we have our B, which is YOH. Now, the variables. They say 28 of HCl. So the volume of the acid is 28 cm cube. React, or yes, 28 HCl react with 4.1 GDM cube of B. So we have the volume of the B first is 25 cm cube. And the GDM cube, which is the mass concentration, let's say, is 4.1. So by now we should know the unit for all the variables. GDM cube is for mass concentration. Instead of me saying mass concentration because of space, I just call it GDM cube. We know what that means. Of an unknown alkali, okay, which is that, whose concentration was 7.0 GDM. We should calculate the molar concentration of YOH. Now, for the last time, for those of you who may want to write it, they say 28 hydrochloric acid, HCl, of concentration 4.1 GDM cube. This is for even the HCl. Sorry, GDM cube is 4.1. Y, that of the base is 7.0. 7.0 GDM cube. Now, we should calculate the molar concentration of YOH, the relative atomic mass of the element. First question, 1. Molar conc of B. So we're going to look at the formula and the variables given. Okay, we have to also balance our equation. Let's call this Na and number of moles of the base. Yeah. So by balancing of the equation, I have my HCl plus YOH will give me my YCl plus water. So we're going to look if the equation is balanced. We have one Y, one is there. Hydrogen are 2 of them. We have 2. Oxygen is 1. And chlorine 1. So it's balanced. The number of moles of acid to base is 1:1. So I'm going to take this out. Now they say we should calculate the molar concentration of the base. We have many formulas which we can use, but one of the most outstanding of them all is the CAVA, which as of right now, we cannot apply CAVA here because we do not have the concentration of the acid. So when we use CAVA, we cannot get what we're looking for because we cannot deal with 2 unknown. Now, it becomes almost impossible if we do not know our way through this whole thing. For us to be able to do this, which we know, we can also use another formula, which is mass concentration over relative molecular mass. Now the mass con is given. The relative molecular mass, we have Y, which is unknown, which means we cannot still even apply that. Therefore, for us to proceed, we must first of all come back to solve for the molar conc of A before we can use that to get the molar conc of B. They wouldn't tell us most of these things, but we should know by virtue of our understanding of volumetric analysis calculations. So, molar conc of B, I would say, to do that, we must get the molar conc of acid. Therefore, if we must get the molar conc of acid first, therefore, the next thing to be done, I will apply my other formula, which says mass concentration over relative molecular mass. I will therefore say molar conc of A is equals to mass conc of A over relative molecular mass of A, which is equals to the mass conc of A is given to be 4.1. I will have 4.1 GDM cubed. The relative molecular mass is 36.5 G mole. Most of us will want to ask, how do you get 36.5? We have to calculate the relative molecular mass of HCl. So if this is my HCl, hydrogen is 1 plus chlorine is 35.5. So when you add that, you have 36.5. That's how we got there. So from here, we will proceed to say our 4.1 divided by 36.5. We now have 0.112. Here is 0.112 mole per dm cube. So this is the Ca, concentration of the acid, which is 0.112 mole per dm cube. Having gotten this now, we have to now proceed. Remember the initial question says the molar conc of the base. Since we understood that we couldn't get that directly, we have to pass through a different pattern to get there. So now we have the possibility of attaining to that visibility by using the CAVA formula. We can get there. So let's see, by application of that formula now, I've gotten this. I want to make use of that formula. Let's see how we're going to get there. So I'm going to take this out. Now, which now says molar conc of B can now be gotten by using the formula CAVA over CBVB is equals to NA over NB. All right. So since I'm looking for the concentration of the base, I have to make it the subject. I have to make CB the subject. So CB in mathematics, making it the subject of formula, I will have CAVANB over VBNA. So by cross multiplication, this multiplied by this and this with this, I divide both sides by VBNA. That is why it is down, why this other side will be clear of. So substituting those variables inside the formula, I will have concentration of the acid, which is now 0.112 mole per dm cube, times volume of the acid, which is 28 cm cube, times number of moles of the base is 1, all over volume of the base is 25 cm cube, times number of moles of acid is 1. So this will be equals to, so I have my 0.112 times 28 divided by 25, 0.125. So my final answer is 0.125 mole per dm cube. So this is the concentration of the base. Cb equals to 0.125 mole per dm cube. Now, the next question says, do you know what that is? Excuse me, let me get it out. Okay. All right, the next question says the relative atomic mass of the element. So for us to get the relative atomic mass of the element, we must first of all know the relative molecular mass of the compound. So by virtue of that, I will proceed. I can clean the board right now. Now, the next question here, let's call it 3. The relative molecular mass of B is equals to mass conc of B over molar conc of B. And this is equals to the mass conc of B is 7.0 GDMQ, while the molar conc is 0.125 mole per dmq. And this will be 7 divided by 0.125 is 56. So 56 G mole. Now, if the relative molecular mass of the whole compound, let me put it here, RMM, 56 G mole, means the relative molecular mass is 56. So now what is Y from this? So I can easily say, I can manage the space. I have YOH is equals to 56. Y plus 16 plus 1, which is 17, is equals to 56. Y is equals to 56 minus 17, and Y is equals to this. So now I have 56 minus 17, I have 39. My Y is 39. Now, let's say, if possible, name the element. Now, what element in the periodic table has the relative atomic mass of 39? That becomes the problem. We have potassium with atomic number 19, mass number 39. Calcium is having mass number 40. Therefore, if potassium is 39, I can easily say this is KOH. This becomes the compound, and the element is potassium. So you may be coming across things like this, and they wouldn't tell you the procedures to go through. They say, take the formula or the question above, solve for this, solve for that. They wouldn't tell you the steps. But you should know by the intrinsic application of what we've been dealing with on a daily basis in terms of the calculations of volumetric analysis to understand the basic principles, and that is key. So at the end of the day, the element is potassium, and the compound is potassium hydroxide. We're going to take another question. Let's see the much we can run. So I have to solve a lot of questions and apply almost all the formulas we've dealt with, so that anytime, any day you're solving or doing your calculations on these, you will not be lost, because you must have come across one or two that deals with what you're looking for. So let's take our next question. Okay. 25.2 cm cube of a 0.0505 mole per dm cube solution of a mineral acid neutralized completely 25 of a 0.101 mole per dm cube solution of a hydrogen carbonate 4 solution. We should calculate the amount of the acid, amount of the base, and the mole ratio. I think I must have solved a whole lot of questions about this amount. So let us just deal with that one. It seems too simple or normal for us. Let's take something else. First, another question perhaps. They said, write a balanced chemical equation for the complete reaction between dilute tetrazosulfate 6 acid and aqueous sodium hydroxide. That is first question A. Then B says, I'm going to take the B, then the A then comes in by the formula of zero because the calculation falls on the B. The B says, if 20 cm of a 0.125 mole per dm cube of H2SO4, let's write that. This is A, and the A is H2SO4. If 20 cm cube of that, 20 cm cube of 0.125, so the concentration here, Ca, is 0.125 mole per dm cube of reacted with a solution of sodium hydroxide. B is sodium hydroxide. Now let's look at it. Calculate the amount in moles of sodium hydroxide required for a complete reaction. So this is all they gave us on B. We are asked to calculate what? The amount. So we know amount can be molar count times volume. Amount can also be mass over relative molecular mass, and so on and so forth. So if that is true, we can't do any of these things from this formula as given. But by virtue of our understanding, we know that in every titration, the volume of the base, VB, is often 20 or 25. Since this one is 20, we presume majorly that is 25 cm, that's the size of the pipette. So we'll call this VB is equals to 25 cm cube. Now, remember, the first thing they ask us to do is to balance our equation. So we're going to balance it to see our NA and our NB. So first question A says H2SO4 plus NaOH. Remember, they are all aqueous. Give us sodium sulfate plus water. All right. Hydrogen here is 3. There we have to, obviously, we have to put 2 here to make hydrogen. 2 here. And 2, 2, 4. So I have 2 hydrogen, that's 4. And my Na will be 2 here. So from this equation of reaction, we know that the number of moles of acid is 1. Number of moles of base is 2. So remember, our deal is to calculate the amount of the base. For us to get the amount of the base, we must first get the molar concentration of the base, multiply that by the volume. The volume has to be in dm cube. And when we do that, we get the amount of the base. So let's proceed. First question has been solved. This is also in aqueous. This is liquid. So the next thing, let us get the concentration of the base. I'm going to, okay. 2. The conc of B in mole per dm cube. We use the formula CABA, CBVB equals to NA over NB. So for us to proceed further, we're going to make CB the subject because that's what we're looking for. So I'll say my CB is equals to CAVANB over VBNE. This is equals to concentration of the acid is 0.125 mole per dm cube. Your units, you have to pay attention to them. Volume of the acid is 20 cm cube. Number of moles of the base is 2. All over, volume of the base is 25 cm cube. Number of moles of the acid, 1. So of course, cm cube will cancel this. So we proceed. 0.125 times 20 times 2 divided by 25. That's 0.2. So our answer is 0.2 mole per dm cube. So CB is 0.2 mole per dm cube. Now, if we've gotten that, for us to get our amount, we just have to apply the formula molar count times volume. So now to the question of the day, which is the amount of the base. I can take out this so that we can do the calculations. Okay. Amount of B is equals to molar count of B times volume of B. Now the volume is always in dm cube, which means we're going to convert the volume from cm cube to dm cube by dividing by 1000. That's very important. So now we move on. We say molar count of the base is 0.2 mole per dm cube. Times volume of the base is 25 over 1000. Put our dm cube outside. So this is, can take this out. Okay, 0.2 mole per dm cube times 0.025. Let me be certain about that. 25 divided by 1000, 0.025. 0.025 dm cube now. So this is 0.2 times 0.025 is equals to 5 times 10 raised to power minus 3 mole. All right? Yes. Now, our answer is 5 times 10 raised to power minus 3 mole. The unit for amount is in mole. But remember also, this dm cube minus 3 takes care of this dm cube raised to power positive 3 by virtue of indices. Number with equal bases multiplied, the powers are added. So minus 3 plus 3 is 0. dm cube raised to power 0 is 1. 1 times mole is mole. So that's how we got here. And this becomes our answer. We're going to take other questions, more questions. Okay, we've treated some questions on water crystallization before now. So we're just going to move straight into percentage purity. All right. Our next question says, A is a solution containing 6.3 GDM cube of impure ethane dioic acid. So the acid is impure. Remember, we're dealing with percentage purity. B is a 0.10 mole per dm cube sodium hydroxide solution. 25 cm cube of solution B gives 20.57 cm cube of A for complete reaction. If the equation of reaction is given as follows, then calculate the concentration of solution A in mole per dm cube, concentration of solution A in GDM cube, hence the percentage purity of ethane dioic acid. So let me list out the given variables before we move out. Okay. Here is a solution containing 6.3 of impure ethane dioic acid. So this is our H2C2O4. That's our ethane dioic acid. And it contains 6.3 GDM cube. So the mass concentration of ethane dioic acid impure is 6.3 GDM cube. of impure A. B is a 0.10 mole per dm cube. Concentration of the base 0.10 mole per dm cube. Sodium hydroxide, okay, still the same there. 25 of solution B gives, so volume of the base is 25 cm cube. They said that react to give us 20.57. Volume of the acid is 20.57 cm cube of A. For complete reaction, we should calculate A, concentration of A in mole per dm cube. Yeah. So the concentration of A in mole per dm cube. All right. They also give us the equation of reaction, which is here. H2C2O4 plus 2 moles of sodium hydroxide will give us Na2C2O4 plus 2 moles of water. Many a time, the equation of reaction will be given. But if it is not given, you have to balance. And you can only know how to balance after a constant practice system. If you practice all the time, you become acquainted with it. So now, from here, the number of moles of acid and base, number of moles of acid is still 1, and number of moles of base is 2 from the equation of reaction. So I can take this out now. Doesn't matter, so that we can proceed. Then, the first question, they say, concentration of solution A in mole per dm cube. Now, I want to get the concentration. Let me write it here. Con of A. How do we do that? We use, let's look at the possible formula to use. Because of the concentration of the base is given, we can now look for the Ca. If we use the CAVA formula, by virtue of what we have, the variables given, that can work. So we can apply that. So I can now say we can use the formula CAVA over CBVB is equals to NA over NB. So my CA, which is what I'm looking for, is equals to CBVB NA over VANB. And this is equals to, the concentration of the base is given to be 0.10 mole per dm cube. Volume of the base is 25 cm cube. Number of moles of the acid is 1. Volume of the acid is 20.57. Times number of moles of the base is 2. So this is equals to, so let's find out what we're going to get. So 0.1 times 25 divided by 20.57 and also divided by 2 is 0.060. So this is 0.060, 60 what? 608 mole per dm cube. I'm going to check that again. Ca, that says 0.0608 mole per dm cube. All right, let me confirm that to be certain. 0.1 times 25 divided by 20.57 divided by 2. 0.0608. Okay. If that is correct, like we have it right, we have to proceed. The next question says we should calculate concentration of solution A in GDM cube. Remember, this GDM cube is for the impure. What we're going to calculate right now is for the pure ethane dioxide acid. And that can be gotten by multiplying mass con is molar con times relative molecular mass. So we have to know the relative molecular mass of this, and we have gotten our molar con. Then when we get that, we've gotten a mass con of pure ethane dioxide before we can proceed further. So let's take out this. Second question, mass con of H2C2O4 is equals to molar con of A times relative molecular mass of A. The molar con is 0.0608 mole per dm cube times the relative molecular mass should be 90 g mole. We're going to find out how. So let's find out how is it 90. We have H2C2O4. Hydrogen is 1 times 2 plus carbon is 12 times 2 plus oxygen is 16 times 4. This is 64 plus 24 plus 2. Okay. 88 plus 2, 90. So if that is true, we can now proceed to put it down. If it is 90, we now say this times that 90, which I've given to us. So let's see what we're going to get. 0.0608 times 90 is equals to 5.472. 5.472. So 3 significant figure, we can take this. GDM cube. So this is for the pure. Let me take the equation so that I can accommodate more. So GDM cube of pure is 5.47 GDM cube of pure A. Now, we've gotten all of this. Let us proceed to the next question. The next question says that we should hence get the percentage purity. Now, that is another formula. What is the formula for percentage purity? We say is the mass con of pure over mass con of impure times 100. So if I apply that, I'm going to get the percentage. At what percent was the substance impure in the process of the reaction? So let us proceed. Now, the next question says, let me start it. Percentage purity is equals to mass con of pure A over mass con of impure A times 100. And the mass concentration of pure and impure, that of pure is 5.47. 47 GDM cube. That of impure is 6.3 GDM cube times 100. Remember, I told us that in the course of our calculation, the mass con of pure is always lower or lesser than that of impure. So at any time you're dealing with this calculation and your mass con of pure is higher than that of impure, note that there is a mistake which you must check to correct. So now what do we have? 5.472 divided by 6.3 times 100. That gives us 86.9. This is 86.9% pure. We're looking for percentage purity. The compound is 86.9% pure at the end of the day. That was a very good one, not that bad. We can deal with that. So let us take another question. We'll solve many questions and see what we can get out of it. Our next question here says, A is a solution of hydrochloric acid containing 5.0 GDM cube. All right. B is a solution of impure potassium hydroxide. Remember what we saw earlier is percentage. Okay, they give us that of the impure acid. But now we're dealing, the impurity is in the base. Impure potassium hydroxide containing 6.50 GDM3. If 25 of B gives 19.10 cm3 of A for a complete reaction, with the equation of reaction given, we should calculate the following. Concentration of A mole per dm3, concentration of B in mole per dm3, percentage purity of B. All right, remember, let's start. Maybe we'll get the rest of the information as we proceed. All right. A is a solution of HCl from the given. A is HCl, while B is potassium hydroxide. This is A. I B is potassium hydroxide. Let's see what we're going to get out of this. A is a solution of HCl containing 5.0 GDM3. The mass count of the acid is 5.0 GDM3. Okay, B is a solution containing impure potassium hydroxide containing 6.5. The impurity is 6.5. GDM3 of impure. 6.50 GDM3. If 25 of B, volume of the base is 25 cm3, gives volume of the acid is 19.10 cm3 of A for a complete reaction. With the equation of reaction given, which is HCl plus potassium hydroxide, give us potassium chloride plus water. So our number of moles of acid is 1, and number of moles of base is also 1. 2, potassium 1, chlorine, oxygen 1. Okay, that's balanced. So with this information, they say we should calculate concentration of A in mole per dm3. Now, we have 3 formulas to calculate the molar count of the acid or of any substance. The other one is amount over volume. The other one is the CAVA, and the other one is mass count over relative molecular mass. In all of these, when we use the CAVA, we can't get this because the concentration of the acid or base is not given, so we can't determine this. When we use amount over volume, we can't still get this because there's no amount given. So the only one we can make use of is the mass count over relative molecular mass of the A. The mass count is given, the relative molecular mass can be determined from here. So in the course of our solving questions on this, knowing one formula will not help. You have to know all the formulas associated to one variable, concentration or amount or relative molecular mass and so on. So let us solve that. 1, molar count of A can be gotten using the formula mass count of A over relative molecular mass of A. The mass count of A is given to be 5.0 GDM3. The relative molecular mass is 36.5, 5 G mole. I told us how we did that. Chlorine is 35.5 plus 1, that's 36.5. So when we move further, we check our 5 divided by 36.5 is 0.137. is 0.137. Okay. 0.137 mole per dm cube of A. So I think that's the first thing they asked us. Now the next question says concentration of B in mole per dm cube. So let me put that here. Ca is 0.137 mole per dm cube. Now they're asking for the concentration of the base. We can now use our CAVA because we've gotten this. When we apply the CAVA, we can get this. So CBA will be this. Let's move on. I can take this out now. Let's say yeah. Now, to con of B in mole per dm cube. We use the formula CAVA over CBVB is equals to NA over NB. So we're looking for CB, which is concentration of the base. We can now say our CB is equals to CAVANB over VBNA. Substituting these variables into the formula, we're going to have concentration of the of the acid is 0.137. 0.137 mole per dm cube. Volume of the acid is 19.1. 19.10 cn cube. Number of moles of the base is 1. All over, volume of the base is 25 cn cube times number of moles of the acid is 1. So this is equals to, let's see what we're going to get, 0.137 times 19.1 divided by 25 equals to 0.105. 0.105 mole per dm cube. So now we have 0.105 mole per dm cube. So we've got to the concentration of the base. Okay, having done that, the next thing says we should calculate the percentage purity of the base. Now, when you look at this, what we've done so far, they've given us the mass concentration of the impure and virtually everything. But now, for us to get the percentage purity, it is important if we still remember the formula for that, which is the mass con of pure over mass con of impure times 100. And the mass con of pure wasn't given, and they never asked us to calculate it. But by virtue of our understanding of the formula, we know that something is missing, which we must have to get in order for us to proceed further to get the percentage purity. Therefore, we have to calculate the mass concentration of the pure KOH. And remember, we said it has to be less than this, which this is that of the impure. Whatever we're going to get should be less than 6.5. If it is more than 6.5, it's either the equation is wrong or we are wrong. So let's find out what that is and see how we're going to get to that place. We have to calculate the mass, concentration of the pure base. So mass con of pure B is equals to molar con of B times relative molecular mass of B. And the molar con of B is 0.105 mole per dm cube multiplied by the relative molecular mass, which is 39. I think everything is 56 G mole. I'm going to find out. Remember, we have KOH 39 plus 16 plus 1. This is 56. Okay. There we go now. We have 0.105 times 56 is equal to 5.88. 5.88 G mole. G what? DMQ. So this is GDMQ, which is 5.88 GDMQ of pure. Now remember, okay, like I said earlier, this is 6.5 must be higher or greater than 5.8. So we are on track. So let's proceed. Having gotten the mass concentration of the pure, and they gave us that of impure, then we can proceed to get what? The percentage purity. So let's say about the percentage purity. I can take this out. Yeah. Oh man. All right. Now, percentage purity is equals to mass con of pure over mass con of impure, impure B, times 100. And this is, the mass con of pure is 5.88. 88, that of impure is 6.50 times 100. And this is equals to 5.88 divided by 6.50 times 100. 90.5% pure. 90.5% pure. We're looking for the percentage purity, and that is what we have. So there will be questions that will be requiring us to find that of impurity. And when the time comes, having gotten this percentage purity, we know that percentage purity plus percentage impurity is equal to 100. So 100 minus this will give you percentage impurity, which is about 9 point something. Let's take another question here before we cross over to redox titration. Excuse me. All right, let's start. In the titration, 25 cm cube of an impure anhydrous sodium triazocarbonate 4, okay, sodium triazocarbonate 4 containing 5.0 gram in 1 dm cube, which is just the same as saying 5.0 GDM cube of solution, when neutralized by 22.20 of 0.10 mole per dm cube hydrochloric acid. We should calculate the molar concentration of the sodium triazocarbonate 4, the percentage impurity in the triazocarbonate 4. So I think this time around they are giving us a question on purity and impurity. So let's take that and see what we're going to get about the impurity. So I'm going to take out this so that I can take another question. All right, so okay. Let's take the question now. Let's list out the given. In the titration 25 of impure anhydrous sodium triazocarbonate 4, so B is sodium triazocarbonate 4. Okay, that's B. The volume of B is 25 cm cube, as given. All right. Containing 5.0 GDM cube. So the impure is 5.0. GDM cube is 5.0 of impure. Let's see. in 1 DNQ of solution were neutralized by 22.20 of A. Volume of the acid is 22.2 cm3. And concentration of the acid is 0.10 mole per dm3. 10 mole per dm3. Of hydrochloric acid. Calculate, okay, the percentage, the molar count of the sodium, that's the molar count of B. So before we move further, we're going to balance our equation, which is, I think this was HCl. Let me be certain before we'll be dealing with something else. HCl, yes. So we have our HCl plus sodium triisocarbonate 4, which gives us sodium chloride plus water plus CO2 gas. This is gas, aqueous, and aqueous. So let's see if our equation is balanced. We have 2 hydrogen there, we have 1 here, so I can begin by putting 2 here. I have 2 hydrogen. Now hydrogen is balanced. Chlorine is 2. Chlorine is 1. Sodium is 2, so I can put 2 here. And I have 2 sodium, 2 chlorine, and that guy is okay. Water, oxygen, we have 4. Is it 4? CO2. This is 2, sorry. That's CO2 is a gas. CO2 plus 1, that's 3. Then this is 3. So our equation is balanced. I have my number of moles of acid here is 2. The number of moles of base here is 1. So with this, they say I should calculate the concentration, the molar count of the acid. Where is it? The molar count of the base, sorry. I should calculate the molar count of the base. So since I have Ca, I can use my CAVA formula to get the molar count of the base. So by doing that, for molar count of B, we use the formula CAVA over CBVB is equals to NA over NB. And our CB, which we're looking for, is equals to CAVANB over VBNE. And this is equals to the concentration of the acids is given to be 0.10 mole per dm cube times the volume of the acid is 22.2 cm cube. The number of moles of the base is 1 all over volume of the base is 25 cm cube times number of moles of the acid is 2. And this is equals to, so I have my 0.1 times 22.2 divided by 50, 0.0444. 0.0444 mole per dm cube of B. Okay, that is the first thing. The next question they say, we should calculate the percentage impurity. So let me put it down first. My Ca is 0.0444 mole per dm cube. Okay, now the percentage impurity. Remember, I said, for us to get the percentage impurity, we must get the mass concentration of both pure and impure. And in this case, they've not given us that of pure, so we're going to calculate it by, this is not for this, sorry. CBA is 0.0444 mole per dm cube. All right, sorry about that. So we're going to calculate the percentage purity by multiplying the molar count with the relative molecular mass to get the percentage what? Purity. And like I said earlier on, it is meant to be lower than what we have here, and here is 5, so I don't know what that value would be, but let's see what it is. So now I want to calculate the percentage, the mass concentration of the pure sodium triisocarbonate 4. So to do that, I say, is it 2 or so? Mass conc of pure B is equals to molar conc of B times relative molecular mass of B. And the molar conc of B is 0.0444 mole per dm cube times the relative molecular mass of this. We have sodium is 23 times 2 plus carbon is 12 plus oxygen is 16 times 3. Okay, this is 46 plus 12 plus, I think, 48. All right, let's put this one 40, 50, 60, 106. So this is 106 G mole. And this gives us, this times 106 is 4.71. 4.71 GDN cube of pure B. Okay, GDN cube of pure is 4.71 GDN cube. So if this is true, like we said earlier on, that the mass concentration is meant of that of pure is meant to be lower than that of what impure, and this has shown truly, although that of impure is very low, which is 5.0, yet we still have the 4.7. So we are good. So let's proceed to get the percentage. What did I say? The percentage impurity. Remember, we can, like I told us earlier on, there are a couple of formulas. Percentage purity is mass conc of pure over impure times 100. And when we get the percentage purity, we can say percentage purity plus impurity equals to 100, and we make that of impurity the subject. But we can also use another formula which is not well-defined. People don't know like that. Percentage impurity can also be mass conc of impure minus pure over impure times 100. So when we check that, we're going to compare to see in both cases and see how that works. So let's check it out and see what we have. We're looking for percentage impurity. Now, the third question says percentage impurity is equals to mass conc of impure minus mass conc of pure. I wouldn't write the mass conc no more, over mass conc of impure times 100. If you check them out, you see that both can still give you what you want. The mass conc of impure is 5.0. 5.0 minus 4.71 divided by 5.0 times 100, and that is going to give us this. 5.0 minus 4.71 divided by 5 times 100. That's going to give us 5.8%. 5.8% impure. So it means the purity level is very high because the impurity is just 5.8. Now, let me call this an assignment. We know the principles which we normally get our percentage purity and impurity. So I would like you to try using the other method, which is percentage purity is equals to pure over. Are we still on? Okay. I don't know if I stopped. Are we still good? Okay, pardon. Remove the phone. Remove the phone. Remove it. Remove it. We're still on. You should have.